So we've done step one, we've created syngas, and now we need to move from the syngas to liquid fuels. And as we move round the circle, then once again we have a catalytic process. But now we already know what that process is. From syngas to synthetic fuels, we can use the Fischer-Tropsch process, and I've just indicated again here the appropriate hydrocarbon synthesis catalysts, which are iron, cobalt, nickel, and ruthenium, to take us through this step. So what you see is that we need to optimize each of these steps given the nature of the reactants we have, and again, the optimization is being conducted using density functional theory. And I know there's only a handful of experts in that area, so let me move swiftly on. So we've now created liquid fuels, and in that process, we're not restricted at all to creating ethanol. We're creating hydrocarbons, so we're creating petrol, and we can create kerosene. As a matter of fact, of course, the part of the world where the Fischer-Tropsch process is extensively used is South Africa, who have developed a coal to petrol plant, and that plant is still in operation. When oil reaches a price of around $70 or $80 a barrel, this process is economically viable. And recently, therefore, the subsidies to Sasol seemed to be paying through. The Sasol process, however, using coal as the starting point, is a very carbon-intensive process. So it's a hot process, requires heat, and it's actually turning sequestered carbon into carbon dioxide in the atmosphere. It's exactly what we're trying to avoid. Whereas in this cycle, we are using that process to generate the liquid fuel that we need. And of course, as we get to the liquid fuel, we find that we've got gas left over. The gas is largely composed of carbon monoxide, hydrogen, and unburnt hydrocarbons. So in that process of generation, we also produce fuel which can be used to run an electricity power station. And that fuel, in effect, in this plant, provides the electricity required for the plant. So what I'm describing to you is a piece of chemical engineering where it's all pulled together. As a matter of fact, the exothermicity in step one is then also used to drive step two, which requires high pressure and high temperature. So we can combine this into a single chemical engineering cycle to optimize the overall energy developed and used throughout the process. And in the end, we put the liquid fuel into a car, we run the car, and we produce polluted automotive exhaust gas. And so, of course, we come to step three, which again is a catalytic step. So we come to the point of the international agreements reached, not internationally but nationally, but very widespread, on exhaust gas legislation. Exhaust gas purification is very much a process driven by platinum-based catalysts, and what we're doing, of course, is taking, it's a three-way catalyst, taking carbon monoxide, NO, and unburnt hydrocarbons again through a catalytic converter so as to produce carbon dioxide and nitrogen. Once we've done that, we go back, of course, to producing carbon dioxide and water vapor, which is the starting point of the whole cycle. I think I've probably exhausted your patience with all of this science. So let me just come quickly to this point. Optimizing each of these catalytic steps requires attempts using thousands of different potential catalysts to find the best for each process. And this is where density functional theory enables one to do at least preliminary testing of a very wide range of systems. And I just show you here from our own work an example where the observation experimentally of rhodium-silver particles providing a remarkable catalytic activity, that observation is confirmed in the density functional theory calculations, and that confirmation then gives us an understanding of why that particular alloy system is good for that particular reaction.